So hello everyone, and thank you for joining this webinar, Development in Chromatographic Separation for Fluorescence Analysis. I would like to start with a few words about MDPI. MDPI has supported the academic community since 1996, and it is the pioneer in open access publishing. Based in Basel, Switzerland, MDPI has the mission to foster open scientific exchange in all forms across all disciplines. Our 469 diverse and open access journals, including 413 peer-reviewed journals and 9 conference journals, are supported by more than 150,000 academic experts who share our mission, values, and commitment to providing high-quality service for our authors. Separation is an international peer-reviewed open access journal on separation and purification science and technology, published monthly online by MDPI. Today's program will start with a few words from the chair, Dr. Kathleen Pero-Abmore, followed by the presentation of our two speakers, Dr. Karen Scott and Dr. Petr Vozka. Afterwards, after the presentations, the speakers will answer your question and the webinar will end with a few words from the chair. Here are some special issues that are relevant for these webinars. You can read more about them on the webinar webpage. If you have any questions for our speakers, please post them in the Q&A box at the bottom of the screen anytime during the webinar. Please remember to add the name of the person to whom you're addressing your question. Now, I will leave the floor to Dr. Kathleen Pero-Abmore from William & Mary, Virginia, USA.
Hi, everyone. Thanks so much for joining us today. My name is Kate Pero-Abmore, and I'm an assistant professor at William & Mary in Williamsburg, Virginia. I'm also the section editor-in-chief for the Forensics and Toxins section of the MDPI journal Separations. And we're really happy today that you're able to join us so that we can highlight some of the ways in which chromatography is used in forensic science. It's probably no secret that chromatography is one of the gold standard techniques used in forensic laboratories, but it's also a really promising area of research. And so today we're going to hear from two really great speakers who are going to highlight some of the research that they've been doing to implement chromatographic separations in their work applied to forensic science. So with that, I'm going to turn the floor over to our first speaker, Dr. Karen Scott. Dr. Karen Scott is the director of the Forensic Toxicology and Clinical Toxicology Laboratories in the Division of Laboratory Medicine at the University of Alabama at Birmingham. And so she's going to share more about her work today. And Dr. Scott, the floor is yours.
So I'm going to talk about some work that we did into an emerging drug, or an emerged drug, called xylazine, which we've been seeing in some of our postmortem, but also in some of our clinical toxicology work here at the University of Alabama at Birmingham. So we see it in our routine work, and the chromatography for this particular drug is not particularly great. So we decided to work to improve that chromatography. So I'm going to talk about the ways in which we did that. As a UAB, as Caitlin said, I'm a UAB employee. I'm the director of both our forensic toxicology lab, but more recently our clinical toxicology lab, reporting data from both of those labs on behalf of the Jefferson County Coroner Medical Examiner's Office, our hospital postmortem lab, and the hospital clinical toxicology lab, and the opinions I'm expressing are my own, so I have no disclosures. So what is xylazine? It's actually a veterinary drug which has appeared in our living and deceased populations. It's a long-lasting, potent alpha-2 adrenergic receptor agonist. So it inhibits the release of dopamine and norepinephrine. That's its primary mode of action, but it also activates the kappa opioid receptors at a low potency, which may contribute to its effects when we see it. We see it alongside primarily our opioid drugs, and our typical opioids are acting on the mu opioid receptors in their primary action, and they do also act on the kappa and delta opioid receptors to lesser extent, but and xylazine is acting on those kappa opioid receptors in a minor capacity. Because we see it administered alongside opioids, we see it in various different administration modes, so smoking, snorting, swallowing, inhalation, injecting, so all of those different ways that it's being administered. And there are some reports that there are some different lesions and things in the population, but we're not typically seeing that in our population here. So part of one of the studies I'm going to mention, we have been interviewing some of the patients and talking to them about their experiences with xylazine, and we're not seeing those wounds that have been reported elsewhere in the patient population here. In terms of pharmacology, it's reported to have an elimination half-life in humans of under an hour, so between 23 and 50 minutes, and a long-lasting duration of action of up to 8 hours. And this is dependent on the way in which it's been administered, and depending on the combination with other drugs as well. In terms of concentrations, that is being seen in humans, this may be partly in relation to the drugs that it's seen with as well. So we don't have a defined safe blood concentration. In cases where it's been seen in non-fatal situations, the concentrations are between 30 and under 5,000 nanograms per milliliter, and fatalities up to 16,000 nanograms per milliliter. And this overlaps, I guess, somewhat with the concentrations that we're seeing in our postmortem cases, which I want to show you in a future slide. So we had actually two research objectives in this particular study. We wanted to look at the prevalence of xylazine in our Jefferson County casework. So we wanted to evaluate our coroner, medical examiner cases. And we did that from 2019 when we first saw it up to the current year. So I actually included data up until yesterday. I did a data dump. Along with our search data. So that's our data from our emergency department casework, which is an ongoing study. And then also the reason that I'm talking to you today is the development and validation of an improved method for detecting and quantitating xylazine by GC-TOFMS. We're in the unfortunate position of not having an LC-MS capability in our lab at the moment. So we're reliant still on GC-TOFMS for our analytical casework. So this here is our objectives for doing this. So we wanted to, because we're looking at patient studies, we had to obtain IRB, get the data from our internal databases. This is for the first objective, and then also evaluate the search data, which is the living patients work. And for the second objective was to, because xylazine has a labile hydrogen, the best way to optimize the issues we were having chromatographically was to determine a derivatizing agent to mask that labile hydrogen, and then develop and validate the method. And also include a solid phase extraction because we're currently using liquid extraction. So we wanted to derivatize and analyze using the GC-TOFMS, and then using our postmortem samples, looking at previously positive xylazine samples and evaluate those using the new method. So just to recap on the positive samples, just to get the kind of database samples out of the way before we go on to the analytical work. To give you an idea of the scope of our positivity since 2019. We just had one case in 2019, that was in June. And then we had a couple of cases in 2020. So it was a slow start for us with regards to our xylazine cases. But then in 2021, we had a burst. So we had over 40 cases in 21. Our optimal year for our xylazine cases was 2022 with over 100 cases. And then it kind of decreased in 23. So we thought we'd passed our peak. And 2023 was actually an interesting year because in terms of our drug overdose cases, that was actually our peak year. In terms of our overdose cases. In 2024, however, we had a resurgence in terms of our xylazine cases, even though we had a decrease in the overall number of drug deaths. And then in 2025, it's dropped off again. And this seems to be a national trend in terms of xylazine overall, but obviously 2025 is not over yet. So we still expect to see some additional xylazine cases popping up. Now, in all of these cases, we typically see xylazine alongside fentanyl, and we don't see it on its own. Typically, we have had one or two cases of it on its own, but those tend to be in farming or agricultural cases where the person involved has access to xylazine because they have access to animals also. But the 98% of these cases have been alongside fentanyl. In terms of our concentrations, they go from our limit of quantitation, which is 25 nanograms per mil or 0.025 mg per liter, up to 36.69. And those cases are actually just because because of decomposition. It's not because those are actually real postmortem concentrations. If we remove those decomposition samples from the pool, our actual range is from below the limit of quantitation up to about 0.95 mg per liter. And also removing those decomposition samples, our average, and also, removing anything below the limit of quantitation, our average concentration is about 0.08 milligrams per liter. Just to give you a case study, and this is the one at our highest concentration. This is a 57-year-old black male, was actually found not long after he became deceased. Resuscitation attempt. They did attempt resuscitation because he was still warm. He was last seen about an hour previously. They found a baggie with the body with a whitish powder, which is typical of these types of scenarios. But you can see here, this is a polydrug overdose. He had a decent amount of alcohol, just under 0.2 grams per deciliter. The drugs of abuse screen was positive for cocaine and fentanyl. So we did detect a reasonably low concentration of cocaine with cocaethylene and other cocaine metabolites. A very high concentration of fentanyl was found along with fentanyl metabolite 4-MPP, and also that very high concentration of xylazine. This was not because, as we said here, the body was still warm when was detected. This was not a decomposition case. So these are real concentrations of fentanyl and xylazine in this particular individual. So very, very high concentrations of drugs. The search study that we're doing, these are hospital emergency department patients. These are patients who come into our emergency department. They screen positive for fentanyl. They're awake and talking when they come in. They voluntarily complete a questionnaire, which includes information about their thoughts and feelings regarding xylazine. They agree to have their discarded biological samples tested and screened for xylazine, and those are sent to the Centre for Forensic Science Research and Education up in the Philadelphia area. The patients are not typically seeking samples for the xylazine presence. In fact, most of them actively will avoid the samples if they think that they would be positive for xylazine. We've had 24 patient results so far, which have all confirmed the positivity for fentanyl. So we've not had any false positive fentanyls. And only 6 of those patients were not also positive for xylazine, despite not believing that they were exposed to the drug. So we do see more prevalence than the postmortem data indicates, with a 75% positivity rate so far for xylazine in this particular population. So on to the reason that we're here, the analytical method. So our current lab method uses a generic liquid-liquid extraction with large volumes of blood, and also uses a helium GC-TOFMS. So at the time, we were concerned about the potential helium shortage. And the method is obviously not targeted for xylazine because it's generic. We look for a large scope of different basic drugs. And fortuitously, the method did pick up xylazine. We did the appropriate method validation for xylazine. The xylazine peak itself does have some tailing due to that labile hydrogen. So our goal was to reduce our blood volume, mask the labile hydrogen, making the method more specific for xylazine, and also we had purchased a hydrogen GC-TOFMS, so we wanted to use that particular instrument for this. So we started by evaluating different derivatizing agents. This slide here shows the derivatizing agents that we started with. We evaluated at a variety of different temperatures, shown on the left-hand side, and a variety of different temperatures also on the left-hand side. We quickly determined that using an acetylation agent was not going to be appropriate, so focused mainly on the silylation agents. So different types of BSTFA, different percentages of the TMCS catalyst, and also tried including acetonitrile to see if that facilitated the derivatization. So what we were looking for was the highest amount of product, and also improved peak shape. We ended up with BSTFA with the 10% TMCS giving us the best results. The reaction is shown on this slide. So basically, and I don't know where, if my mouse, is my mouse showing up on this slide here?
Yes, we see it.
Okay, perfect, thank you. So our labile hydrogen is just over here in the middle of the xylazine here. So we end up with our trimethyl silyl group just attaching onto the xylazine here. So we're masking this particular nitrogen here with our TMS. So this is our workflow. So we are moving from a 5 milliliter extraction to a 1 milliliter. We also are moving from a generic internal standard to using xylazine D6 as our internal standard. We add our buffer. We are vortexing our sample, doing our solid phase extraction, evaporating using a sample concentrator, and then doing our, once the sample is dry, adding 100 microliters of our derivatizing agent for 60 minutes at 80 degrees centigrade, which is a long time. It was a derivatization that does need quite rigorous temperature and time in order for the derivatization to go fully prior to our GC-TOFMS analysis. The solid phase extraction itself worked well with a generic Bondilute certify extraction, which works well for us because we see xylazine so frequently with fentanyl. This extraction also works well for fentanyl. So it's just a standard opioid solid phase extraction from UCT. One downfall that has happened recently is that dichloromethane has now been banned from the lab. So we are actually in the process of revalidating or re-verifying the extraction and replacing the dichloromethane with another solvent. So that was an unfortunate thing that happened at the beginning of the year, that we had to replace the dichloromethane. But at the time that we did the research, we were using dichloromethane for the elution step. So this is the kind of standard solid phase extraction that was used at the time of verification for this extraction. So the method was validated per ANSI ASB standard 036. Was linear from 15 to 200 nanograms per milliliter. The bias and precision were less than 20%, and it passed all of the other criteria. So dilution integrity, carryover, stability. The recovery was greater than 80%. There were no interferences, and the limit of detection and quantitation were as shown on the slide here. So what happened with the derivatization is shown nicely on the slide here. So on the left-hand side was the chromatography of xylazine on the method that is used in the generic liquid extraction. And you can see that tailing for the xylazine peak, which is corrected after the derivatization with the solid phase extraction on the right-hand side, and the selected ion monitoring semions are shown also with the +72 with the TMS. Also, the same type of column, it's a 5%, it's a standard 5% GC column, but we're using a thinner film thickness due to the switch of carrier gas from helium to hydrogen to optimize the separation. So the final thing that we did, which we thought would be interesting just because there's not a huge amount of information on the scientific literature about it, was to compare central and peripheral blood. We obviously wanted to verify the method on authentic postmortem samples, but we also thought it would be interesting to look at both central and peripheral blood samples using the method. So we took paired samples from a variety of cases for central and peripheral bloods and ran them using the new method, and established the central to peripheral ratio. And in 11 of the 14 cases, there was higher concentrations in the central blood than there were in the peripheral blood, indicating that xylazine may well be undergoing postmortem redistribution. So we can see the central to peripheral blood ratio on the final column here. In some of the samples, the concentration fell below our limit of quantitation, so we were not able to establish an actual ratio. But also was able to show us that for some of the cases, we are able to detect concentrations below our limit of quantitation, which is useful. And remembering that on the previous method that the limit of quantitation was 0.025, so our method is definitely more sensitive than the previous method using the helium GC-TOFMS with the tailing and using 5 milliliters of blood. So in conclusion, despite declining since 2022, our overdoses had increased again in 2024, but we're seeing a decline again in 25. Xylazine is typically seen in combination with fentanyl in our postmortem cases, but also in our antemortem cases, with 75% of the emergency department patients having xylazine on board, despite thinking that they're not being exposed to xylazine. So it's very prevalent, even in our living population, thinking that they're actively not seeking xylazine. Our newly developed method shows improved peak shape, increased sensitivity, and a more accurate way of measuring xylazine in postmortem toxicology. And results from our central and peripheral positive xylazine samples indicate that postmortem redistribution may be occurring for xylazine. I'd like to thank many people for helping with this study. First and foremost, my forensic toxicology lab staff, my lab manager, Jennifer Whiddon, my staff, Andrea Shipley and Hannah Hines, and previous staff, Susan Cloda. Also, Jacqueline Mullins, who was the master's student who was responsible for doing the method validation, as well as her, the other members of her research team, Dr. Elizabeth Gardner and Dr. Daniel Dye, Chief Bill Yates, who's the Deputy Coroner at JCC MEO, UEB Department of Pathology, who provided research funding for the method development study, UEB, Frank Bearfield Department of Criminal Justice, and finally UEB's search team, who have worked on the emergency department study. And finally, everybody here for listening and also for inviting me to do this presentation. Thank you.
Thank you very much, Dr. Scott. It was a really interesting presentation and such an important topic right now, as so many of the points that you highlighted. I know that there's going to be some questions, so just as a reminder, you can put all of your questions in the Q&A box, which should be at the bottom of your screen. If anyone has any trouble with that, you can always message one of us or the journal staff. And with that, that brings us to our next speaker. So our next speaker is Dr. Petr Vozka, who's an associate professor of analytical chemistry at Cal State LA, Los Angeles, or Cal State. University, Los Angeles. And he also directs there the Complex Chemical Composition Analysis Laboratory, or C3AL. And today we'll be speaking to us about estimating fingerprint age using GC-TOFMS. Peter, the floor is yours.
Thank you. Can you see my screen?
We see
Yeah.
it.
Okay, so what I'm going to share with you today is very preliminary, especially compared to Dr. Scott's research. But I want to kind of share with you the story behind why we're doing this, because I'm not a forensic scientist expert at all, but I want to kind of give you the story and some of the results that we were able to get. So Coastal LA is very special because we don't have PhD students. We have mostly first generation students. And so most of my students are undergrads, and sometimes, if I'm lucky, I have some master students. All of this data, all of the research that I'll share with you, is being done by undergraduate and master students. Now, the Coastal LA is also special because we have a Herzberg Davis Forensic Science Center on our campus. And it's kind of unique building or structure for me because at the very first floors, we have the laboratories of the Los Angeles County Sheriff's and Los Angeles Police Departments. So real cases are being actually done, and solved there. On top of it, there is a California Forensic Science Institute, and what Coastal LA did, I don't know how many years ago, but they built, on top of all of this, they built a School of Criminal Justice and Criminalistics. So students can get their master degrees in this building, but they also go, to the lower floors to work and kind of learn from the real experts. And because of this, I kind of thought about what we can do. And so my expertise is gas chroma. That's how I see myself as having expertise in gas chromatography and mostly comprehensive two-dimensional gas chromatography. So in partnership with LICO, we set up a LICO call facility on our campus. And the goal of this facility is, to train and do research with undergraduate master students and faculty that are part of our campus. So because of LICO, we have a multiple instrumentation. I don't know if you're familiar with these, so I go like very briefly through those. But we have a one-dimensional and two-dimensional gas chromatography, and we have different type of detectors. The one I'm going to talk about today is the mass spectrometry. In this case, is the time of flight mass spectrometry detector. We also have a multiple softwares which are pretty cool because you can, for instance, compare samples, before and after, or if you collect samples within, several days, you can kind of, in the software, you can process the data very quickly to see which compounds are decreasing, increasing, and so on. So it's very helpful, especially in this kind of type of research. And because of our capability, we are lucky to collaborate with two people from the School of Criminal Justice and Criminalistics. One of them is Katrin Roberts, who's also the director of the master program there, and she's also the executive director of the California Forensic Science. And the other one is Dr. Vargas, who's the associate professor there. And because of them, we work on two projects currently. So one of them is the forensic timing of alcohol use using epidermal biomarkers. So basically, we are trying to find, or we are trying to see if there is a way to find, if there is a way to kind of predict or tell when a person used alcohol from the human fingerprints, because we can measure obviously the alcohol content in the blood and so on. But the question is if we can kind of say like this person used alcohol, 7 days ago, 14 days ago, some stuff like that. And the project I'll talk about today is the kind of estimating the fingerprint age at the crime scene using gas chromatography. Again, this is very preliminary. I'll go over a little bit of the background for those who are not familiar with the fingerprints. But basically, fingerprints or latent fingerprints are those that you can you see on your screens and everywhere. And these are usually those before you kind of touch your face or your body. On the other hand, the groomed fingerprints, these are when you start touching, your face, and you these are more concentrated in different type of compounds, and these are the fingerprints we usually work with. The reason behind this is that the fingerprints analysis kind of traditionally involves comparing latent fingerprints to known prints for identification. So basically what forensic scientists do right now is they kind of look, at the picture. And the chemical analysis of the fingerprints is not yet kind of commonly implemented in routine forensic assessment. And because up to 65, some literature says, 70% fingerprints found at the crime scenes are actually unusable for identification. So basically the goal or the kind of the primary objective that we are trying to reach is to kind of develop aging models so we can accurately determine when these fingerprints were deposited at the crime scene. Now, this capability would, greatly enhance investigative accuracy by, validating or refuting subject statements regarding their presence. So, for instance, subject could be, present at the crime scene before the crime happened. So if we can somehow time this and prove this, that would be kind of the ultimate goal. Now, fingerprints are mostly composed of lipids. We are also lucky to collaborate with a different group in Czech Republic. They already analyze, I would say, millions of fingerprints. They focusing on human scent. What they discovered is that whenever you take the human scent from whatever part of the body, it's usually very similar. So, fingerprints and anywhere else in your body, the chemicals are very similar. They were also very successful to predict gender, race, and all the other kind of stuff using the fingerprints or the human scent. So that's why we kind of started doing this, because we know that there is a huge background and there is a lot of kind of literature regarding the chemical composition of fingerprints. And so what we decided to do is we had to kind of select compounds that we're going to target for our aging model, because doing non-targeted analysis would be very complicated at the beginning. We might have to shift that way, but we went through the literature and we kind of figured out that people usually target two analytes. One of them is squalene and the other one is cholesterol. The kind of advantages is that these are abundant in most fingerprints. And we also have we know how the decomposition products look like, and these are usually stable. So that's kind of good to know. And then the way we usually, or the methodology we always follow, is that we have to collect the samples first, then we age them or somehow process them. I'm going to talk about two studies. Then we have to extract the samples, and then we, of course, analyze the extracts. So the collection, nothing surprising. We have always, for every study, we have X number of donors. They deposit Y number of groom samples per donor. And the way is always the same. They wash their hands, they'll air dry them, then they kind of, take the groom samples and then place them on the glass slides, which are being pre-cleaned. And then we kind of control the environment of the glass slides. I'm gonna skip the aging because it's gonna be different for these two different studies, but I'm gonna go to extraction. So the goal is also for this project is to kind of follow or do not kind of overcomplicate the way the samples are treated. Ideally, if we can use the same techniques, the forensic scientists or the crime scene investigators use, that would be ideal. So that's what we're trying to do. So we're using medical swabs and extraction solvent. I'm going to talk about the solvents in a little bit. We soak the swab in the extraction solvent, wash the slide, then we kind of we cut the swab tip, we vortex it in the extraction solvent, then we put it in centrifuge basket. We get all of the liquid basically out of the swab. Then we transfer all of this to GC vial. We have nitrogen evaporation unit, so we evaporate all of the solvent, and after that we add a controlled kind of volume of a solvent with internal standard. And then after this, it goes, in this case, to GC-TOFMS, but we also start doing two-dimensional gas chromatography with time-of-flight mass spectrometry. So for the GC-TOFMS, we are using Lycos GC-TOFMS. Here you can see some of the conditions. The splitless injection of 1 microliter might seem crazy, but it's working for us. We have no sample overload. The oven program, because we targeting 2 compounds, so it's a little bit kind of fast, but we can kind of do that because this is not non-targeted analysis, and you can see kind of all of the other data. We're using Chromatograph software to process all the data. Chromatograms could look like this, for instance. What I didn't say is that our internal standard is 1 decanol, and then we again target squalene and cholesterol. So in the first study, that was the original study when we kind of tried to see if we take, different fingerprints, if these 2 compounds, because again, they biodegrade, they also evaporate, they have different boiling points. So the question was if the kind of peak area ratio, if the concentration between these 2 kind of follow a similar pattern for different people. So in this case, we only had 2 donors. We collected, I think, 36 samples. We had no control over the surface area. That was kind of that's what we wanted because again, we wanted to simulate what could happen, at the crime scene. So if you collect the samples there, these samples might not be full, kind of thumb samples. Sometimes the sample might be, smaller in volume, sometimes could be larger. And that's why we're also doing the peak area ratios, because this would not be dependent on the concentrations. And we use the ambient lighting conditions. This is important for the next study. Now, as you can see, both donors exhibited like similar pattern as the concentration of cholesterol and squalene fluctuated. There are differences in maximum peak areas, possibly due to the difference in the initial amounts of lipids from each donor. And there are obviously like visual variations between these 2 samples. And so what's we kind of start thinking here that, the donor's diet, gender, lifestyle habits, and all of the other things may play a role. But there was a similar pattern. So we decided to kind of start looking into the environmental factors that affecting the aging, which you can think of, all of these: temperature, airflow, humidity, all of these. And so what we wanted to kind of test also is if we take 3 different lighting conditions, for instance, if that would play a role on these peak area ratios. So we selected like simply 3 lighting conditions. One was the LED light, the other one was no light, and then the third condition was the regular ambient natural light. So, approximately 12 hours light, 12 hours dark. Then what we experienced, as Dr. Scott mentioned, is that the DCM was banned in US. So we had to find a new solvent, which is not that hard if you do targeted analysis, because you can kind of test your new potential candidates. Might be way harder for untargeted analysis. But doing few tests, we kind of find that the 3:2 volume ratio of hexane and isopropanol mixture is kind of ideal for our 2 compounds. It kind of overperformed DCM in these kind of extraction steps. And then, so this took us some time. We had to, redevelop some of the methods and the extraction protocol. But after this, we proceed with the kind of light study. So here the objective was to kind of evaluate whether the proposed method yields consistent run behaviors across different donors when exposed to different light conditions. And in this case, we only had, again, like 3 donors. Each of them provided 20 groom samples, so 60 samples in total. In this case, we kind of control the sample surface area. And as mentioned, we had 3 lighting conditions. So this was the aging, and we aged the samples from 0 to 20 days. Again, very preliminary data. We had 3 donors. Donor C, unfortunately, didn't show any cholesterol concentrations in the sample. So that was a huge that's a huge deal for us, as the cholesterol might not be the best kind of molecule to target. For the donor A, the full light ratios were up to 100 times higher than the ambient and dark, but the ambient and dark trends were statistically indistinguishable. The full dark showed a linear decline, unlike the sinusoidal trend of the light exposed samples. Donor B, the trend behavior was similar across all lighting conditions, especially between the ambient and dark, and kind of comparing those 2 donors, which that was the goal. So there are statistically significant differences in ambient and dark ratios between donor A and B. So what we also notice here, what you can notice here, that the divergence between their trends was especially evident between the day 0 and 6. So that kind of suggests that we should kind of time point that part, or that time little bit kind of we should sample there way more. So although the proposed method didn't yield kind of fully consistent dream behaviors, this kind of analytical approach still remains promising, and we still will be kind of exploring this. What the goal for us is to do next is we need to kind of increase the sampling frequency in early aging period. That means, between the day 0 and 6, that can kind of could clarify the initial difference between these degradation behaviors. We obviously need a larger donor pool, like having 2 or 3 donors. That's not enough. So we definitely need to increase the larger donor pool, but we don't want to do it until we really have, kind of perfect methods and extraction steps, and once everything is really aligned. As donor C didn't show any cholesterol in the samples, we definitely might need to think about targeting additional or alternative biomarkers. For this, we are lucky having GC by GC, time of flight mass spectrometry. So we'll be exploring what else we can do there. And then, we definitely need to kind of optimize the method for low abundance donors, because the cholesterol might be there. The thing is that we might not just seen it. Again, as I said, very preliminary, but if you have any ideas, or if it is, have like inspire you what to do, let me know. I'll be happy to talk and discuss. These are my students who collected all the data, who are working on these projects. Elena started all of this 2 years ago. She now moved to her dream job into the crime lab. So my students, they do really a great job. And I want to thank all the sponsors that kind of supported this lab and this research and training center. And if you're interested in human sense, in a GC and GC by GC, then there is a conference we're organizing with Dr. Pearl Upmore in January. The registration is free, so feel free to come and listen more about these forensic science applications. Thank you.
Great. Thank you so much for sharing these interesting applications. It's really exciting to see all the different ways that chromatography are being used in both of your work. So we have a couple questions, and just as a reminder before we jump into questions, that there is a Q&A box at the bottom of the screen. So for anyone who maybe joined late, don't hesitate to put your questions in the Q&A box, and I can read those out to the speakers here momentarily. And we have a couple already collected, and I've got another one which was sent to me. So with that, I think we can start with Dr. Scott. So a couple of questions for you, Dr. Scott. The first one that came in was whether you've considered implementing any solid phase micro extraction approaches in place of the solid phase extraction approaches that you mentioned. You're on mute again.
I keep forgetting that button. So in my previous job, we did a couple of SPME research projects, and we had some limited success with that. But I think the in terms of ease, the solid phase extraction for the lab staff, because we have multiple samples that we're processing at once, is easier to manipulate than SPME. Like we don't have like a robot that we can use for the SPME. So for multiple sample purposes, SPE seems to be preferred. I don't know about that. I've never done like a costing exercise for the SPME, but so I guess short answer, I don't know how many forensic labs are using SPME as a preferred tool. I mean, I've not tried SPME for xylazine, but I think SPE would be preferred. But I think longer term, as you know, if we were to go down the route of getting LCMS, it's still sitting there on my wish list. But you know, we would be go down to much smaller samples, so we would be definitely looking at changing out how we're doing the sample prep on a wider scale anyway, and maybe moving away from those kind of types of extraction anyway to more of a, not dilute and shoot, but definitely removing that type of extraction to reduce costs anyway.
Yeah, I think that's definitely like from my knowledge base anyway as well, kind of a lot of like toxicological analyses still rely on a lot of solid phase extraction. So I guess until you see that SPME, you know, robotic system moving into those spaces, it's hard to think about, you know, whether that would really be truly adopted, I guess.
Yeah. Mhm.
Yeah, interesting.
Yeah, and I think the pure SPME where you're relying on volatilizing the sample as opposed to the ones that are dipping into the
Immersion.
sample,
Yeah.
the immersion ones. But I think a lot of labs are moving away from solid phase extraction to more of a not dilute and shoot, but like crashing out the samples and that type of thing. So you know, more of a miniaturized, and there's the supported liquid extraction types of phases that a lot of labs are using as well. So there's different options to use to clean up the samples for sure.
Yeah, and I think we're seeing kind of a lot of that shift in environmental analyses as well right now, right, for away from solid phase extraction to other things. So it'll be interesting to see if that kind of changes suit in some of the forensic spaces as well.
Yeah.
Yeah,
But yeah,
interesting.
that was yeah, interesting question. Yeah.
There was one other question as well about your presentation. You mentioned about using like hydrogen in your GCMS protocol. Is there any worry about the hydrogen being used as a carrier gas, like interacting with your derivatized product? Like any potential reactions that could exist there or desulfurization? Have you seen anything like that?
We didn't have any issues with it. And the no, we haven't had any concerns. I don't know where we would see desulfurization. So I mean I don't know that we have any drugs that would cause an impact with. So and it wasn't anything that when we were looking at implementing that was raised as a concern. So I mean we definitely saw, I mean that kind of peak sharpening that we were expecting due to the higher flow rates. And like I mentioned, you know, we were concerned with the reduced volume, that we were just gonna not see anything. You know, going from 5 mils to 1 mil is a concern, right? So we you know when we started doing the work, we were like, we're just not going to see anything, right?
Yeah.
But you know, we were able to lower our limit of quantitation, and still see what, you know, the xylazine, because it is something that we see in lower concentrations in the samples. It's not like we're analyzing Tylenol or something where it's people are taking grams at a time. So we were quite surprised that the project worked at all on this system. And particularly, we are looking at fentanyl on that system as well, and we're seeing down to the types of limits that we're equivalent limits to what we're seeing on the other GC as well with our fentanyl as well. So it's doing what it should be doing with
Yeah.
the film. Yeah.
Yeah, it was really surprising to me to see the data you all have collected on like the prevalence in living individuals,
Yeah.
from the biospecimens that you collected, and especially with them, just thinking that there's no way they've been exposed to that. That's really interesting data.
Yeah, I think especially because from the questionnaire data that they're actively avoiding samples that they think might be laced with xylazine, and there was nobody that thought that they were exposed to it, and 75% were. So the studies are opposite, right? Because on the one hand, we're looking at from the postmortem data, these are 98% of our xylazine cases have fentanyl, and then the other way around, it's like 75% of the fentanyl has xylazine. So that we're not comparing apples with apples. So and this population are actively avoiding xylazine, and 75% of them actually had xylazine in their fentanyl. And
Yeah.
that's so why we're not seeing it in our decedents so much is curious, but so it's definitely not responsible for killing our decedents. So we're not sure why there's that discrepancy, and it might just be that our GCMS method isn't sensitive enough to pick it up at those lower concentrations, because a lot of the emergency department samples are urine, so it might be that we're not sensitive enough compared with the LCQ-TOFMS that the CFSRE is using to test those samples.
Yeah. Yeah, really interesting. I think it's really powerful. Like, I mean, it's great to develop new methods. And of course, in the work that we all do, that's what we spend so much of our time doing. But I think it's
Yeah.
really interesting and powerful to then pair that type of method development with these like occurrence
Yeah.
studies. So yeah, thank you very much for sharing that work. It's great. Okay, so with that, I think we'll flip over to Dr. Vozka and the questions that the audience has for him. So the first question for you, Dr. Vozka, is there a way for you to know whether a donor might be on any type of like cholesterol medication that could affect the way that that marker looks in a fingerprint?
Yeah, that's an unbelievable great question. So since we don't have the IRB yet for this study, that's why we don't have, such a large pool of participations. We're working on it. So yes, of this student actually, or this person was actually on a cholesterol medication. So kind of the conclusion was that that was the reason why we haven't seen any cholesterol. And these are all the kind of things we have to think about while we preparing the IRB, because once you start the study, it's kind of then too late to kind of implement all these questions once you're collecting the data from the people. So it's a great question, because this was really controlled, was 2 or 3 people giving samples. So we were able to kind of pinpoint the reason why not. But it also kind of brings, the awareness of developing aging model based on a molecule that might be kind of eliminated from your body by medication. It's maybe not the best idea.
Yeah, that makes sense. And I guess in a forensic scenario, like if you're looking for a fingerprint at a crime scene, you don't necessarily know that the donor in that situation is on these types of medications. So, having that as part of your study is also a valuable piece of information, I'm sure. Another question for you, Dr. Vozka. This one is actually just for me out of interest sake. So we do a little bit of fingerprint research in my lab as well, with residue. And one of the things that we think about a lot is the fact that a lot of what's known about the chemical components in fingerprint residue is coming from one-dimensional GC analysis. And if you look across the literature at the chromatographic results, there is a lot of coevolution in those samples. And so you can see that sometimes there are like higher level components that are obscuring smaller components. But a lot of what we know about things like aging, the fingerprint itself, or aging the donor, whether like pre or post pubescent, a lot of that information is based on 1D GC data. And one thing that I think about a lot is like, do you think that there are other markers within fingerprints that could be valuable if we kind of move more to a multidimensional GC approach, where maybe we uncover other things or are able to quantify them in a different way than a lot of these preliminary, 1D GC, not preliminary, things that have been done in the past have uncovered?
Yeah, I kind of like my, whole background is alternative fuels, which are also very, very complex mixtures. And all of the assumption there also, everything came from one-dimensional GC. All of the ratios, all of the concentrations were only based on what we could see. Now then shifting to GC by GC, now, in this world we can predict fuel properties, density, stuff like that. And I think it's very similar with basically any application. If you, put on, very complex sample, if you put, another kind of level of separation, you can definitely uncover other markers and other stuff you can see there. Also, people all discuss the squalene and cholesterol because we have standards, so we can kind of safely say this is, cholesterol, this is squalene. And with 1D, you really limited, as you mentioned. So we hope so. We believe our plan is to now run, when we target the compounds, we usually use one-dimensional GC because it's, quicker. You don't need like cooling, liquid nitrogen, stuff like that. Once we do untargeted analysis, or we want to see a little bit more about the sample, we run it through the two-dimensional GC. So we hopefully, yeah. The group I mentioned, they predict, gender and all the other things based on the human scent. They obviously use GC by GC, and they have, tons of data that then they process and develop like these models. And they don't predict these things based on two compounds, of course. So all the other compounds play a huge role in this.
Yeah. Yeah, really interesting. Some like, I guess, less traditional type of forensic evidence from a crime lab analysis perspective, but certainly interesting things to be thinking about in the future of how chromatography is used in the forensic sciences. Okay, and with that, I think that concludes our Q&A. I'm not sure if there are any other questions. I think I've completed all the ones I see.
Yeah, there are no other questions, so I think we can stop here. Thank you everyone for joining today's webinar. Special thanks to our chair and our speakers, and I hope everyone has a great day.